A very good afternoon to everyone and a happy Labor Day to every one of us here. My name is Suhaimi and I am from BEX Asia, organized by RX Singapore. So thank you everyone for taking the time to attend our third masterclass of 2024. We had an overwhelming response in terms of this particular masterclass. I believe the topic heat pump is really interesting. So that's why we had so many people from not just Singapore, but we had people registering and entering this masterclass all the way from Southeast Asia, Philippines, Thailand, Indonesia, Malaysia. We also have people who have signed up from India, North Macedonia. I find it interesting. Switzerland, the US, and some other European countries. So for those of you who are further west, and it might be really early in the morning, and if you are here with us now, I thank you very much. Now, we are excited to have today's masterclass presented by Johnson Controls on the topic of maximizing heat pump potential, exploring cutting-edge commercial strategies for efficiency and sustainability. With us today, our first speaker is Mr. Luke Timmins, who is currently serving as the Senior Director, Commercial and Renewable Energy for the Sustainable Infrastructure Division of Johnson Controls. Prior to this, he was CEO for a Vietnam-focused solar platform owned by investment management firm Vina Capital and Vice President in the Infrastructure and Energy Division at Australian investment bank Macquarie Capital. Luke is a strong proponent of the notion that net zero as a service solutions and renewable technologies have a crucial function in addressing several prevailing global challenges such as climate change mitigation, SDG 13, and energy access issues, SDG 7. He is passionate about transforming energy infrastructure with as-a-service offerings across areas such as cooling, refrigeration, and digitalization. Luke will also be joined by our second speaker today, Mr. Chia Peng Kiang. Now, Mr. Chia has more than 25 years of experience in industrial refrigeration business, starting as a project and design engineer when he joined Graham York back in 1996. He proceeded to gain experience in doing technical sales and later managed a sales team to cover the Southeast Asian regions as a head of sales for Johnson Controls International. Chia's expertise resides in industrial knowledge for system integration and contracting experience pertaining to the F&B industries, such as refrigeration solution for poultry plant, dairy cooling system, ice cream freezing plant. I really need that. It's a hot day. Brewery and beverage industries, industrial cold store systems, heat recovery, and heat pump application. Currently, Mr. Chia leads a team of application engineers to support frontline sales for the Southeast Asia IR markets. Mr. Chia is currently based in Singapore and holds a Master's of Engineering from NTU and a bachelor's degree in Mechanical Engineering from NUS. Can I invite both of our speakers to come on the screen with your microphones and your webcams turned off just to say hi to our audience here today? Hello, Peng Kiang, and hello, Luke.
Hello, everybody. Thanks for joining.
Right. Luke, are we able to have you on the camera, Luke?
Can you guys see me now?
Yes, we see you and we hear you. Hello, Luke. How are you today?
Very good, thank you.
Great.
Yeah, fine. Thank you.
Okay, so both our speakers are raring to go. Now, but before we start the session, a few housekeeping announcements. Now, ladies and gentlemen, should you have any questions during the presentation, please use the Q&A function within Zoom. We have also received a number of questions during registrations, and together with those questions, we shall take it at the end of the masterclass, time permitting. Now, well, with that, let me hand it straight over to Luke. Luke, take it away.
So good afternoon, everyone. Thanks for the excellent turnout today.
Luke, we lost you there on audio.
What about now? We good?
Yes, now we are good.
All right. I was just saying, we're here to talk about heat pumps today. Looks like we've got over 100 people joining. Welcome. Let's go to the next slide and jump straight in. So, thanks for the introduction, Sahami, before. I run a team at Johnson Controls that focus on sustainable infrastructure technologies. And what that means is, in addition to heat pumps, we do other things such as renewables, fire security controls, um, chillers, lots of things. And we put a solution together that ultimately delivers a decarbonization solution and also some financial savings. Today, I kind of wanted to start by giving my broad view of heat pumps and what I'm currently seeing in the market, some of the deals that we're doing. It's quite exciting. We've really seen a lot of growth in this area, which is quite interesting because it's a legacy technology. I mean, our brands York and Sabro have been around for more than 40 years. This is not a new sort of line of product. I think that one of the things that that often comes up when we're having discussions is around technology risks. And I think that because of that history, this is not really a factor when you're sort of going out for project finance or trying to convince a customer on adopting this technology. What I do see as a number one challenge when it comes to sort of implementing the technology is the engineering and the implementation risk. I would say that one of the the key issues here is that you're effectively having to enhance or upgrade, or in some cases re-engineer a customer's heating and cooling solution, and that has to be done properly. So in some cases it could really be a plug and play solution. In most cases it does require some enhanced engineering done by the right people. Now my colleague Pankyang will go into detail on this, but it's definitely something that we find new market entrants don't have a grasp on some of the sort of these implementation risks and the pre-engineering that needs to be done. In terms of financing, as I said before, I mean, legacy technology, obviously improvements year on year, but it was very surprising to me to see that, it's not more prominent in the market. It is a very higher capex relative to a boiler. And I think this has been one of the challenges for adoption. So one of the things that we do in my team is we combine the capital arm of our business, Johnson Controls Capital, and we offer financing solutions in certain markets for certain projects. And typically, we could look at, say, a 10-year financing term, but if we need to sort of make those repayments lower than the current servicing of or operating of a boiler, we could effectively put a 20-year amortization schedule attached to that. So I think these are some of the tools that we've seen have really helped the adoption, and we've seen a lot of increase in orders and also sort of interest in implementing the projects. Regarding the environmental benefits, it's important to know that you're sort of shifting the responsibility from scope 1 to scope 2 emissions. If, let's say, an industrial manufacturing facility has a boiler, and they could be using natural gas, or they could be using oil, on-site fuel, then if you're shifting to scope 2, you have to be very careful. Often I get asked, what's the CO2 reduction, or what are the kind of overall scope 2 emission reductions, and it really depends on the grid that you're dealing with. So in some Southeast Asian countries, the grid could be 700 to 800 grams per kilowatt hour, whereas let's say in Singapore it's almost half that. And if you're shifting the heat pump to sort of use the electrical grid versus sort of an on-site fuel, the sort of the generation mix has an impact, especially if it's a coal-intensive grid. So I guess my next point is if you combine this with renewable energy, whether that be on-site solar, other technologies like energy storage, fuel cells, this could be a very good combination if your sort of target is to reduce emissions, and that's very important to your client or the national regulatory framework. It also, water reduction is definitely a factor here. And then I suppose the other thing that's, we're noticing is very important to the market is compliance with certain certifications like Singapore's Green Mark, LEED. And always the key factor when we're having these discussions or giving inputs to customers or internal teams is that heat pumps have a very high COP, and they generate way more heat, thermal energy than the electricity that they're drawing. So these are sort of important calculations when we're helping customers with the regulatory framework. Just go to the next slide, please. So as I mentioned before, I'm in a team that put all these solutions together. We recently bought some of the first financing deals into Southeast Asia. Why am I mentioning this? Beyond just the narrow heat pump topic, because what we see in the market now is not just a facilities director coming to us for a product or even an engineered product. We see a lot of stakeholders alongside those facility managers, such as a CFO or a chief sustainability officer, that demands that we give a whole infrastructure as a service solution or a net zero as a service solution, alongside the heat pump. So we find now that it's not just about narrow focus on heat pumps. It's about adding scope 1, scope 2 emissions calculations. It's about adding let's say a chiller upgrade, some HVAC optimization, and some renewable energy, helping with green attributes. So heat pump is definitely a growing piece of the puzzle, but we find that it has to be an integrated solution to sort of satisfy what the customer is going for. Yes, there are standalone deals, but just based on the deals that we've closed and the projects that are up and coming, it's part of a broader mix and a financial savings play and a emissions reduction play. Next slide, please. So I'm just wrapping up here. So just a little about us. We're almost 140 years in the business. We have 100,000 people globally and 800 people in Singapore and many more across broader Asia. So I think if there is interest on the call to work with us to identify projects and synergies, we're very happy to assess that and see if we can further the adoption of heat pumps. So that is it from my side. I will hand over to my colleague who has some exciting case studies and very kind of specific information on heat pumps, and I'll be available for the Q&A shortly. So thanks everyone, and see you soon.
Thanks, Luke, for the great introduction, and also Suhaimi. Let me share my screen a bit about heat pump. Yep. So my topic is basically zooming into the technical aspect of heat pump, just to explain a bit about how heat pump works and how product types we have around in JCI, and how we actually do some case studies for heat pump so that we can understand how we can apply cooling and heating and some sort of a payback to understand where do we hit the application of this heat pump in general for our industries around Southeast Asia. So I will bring in about 30 minutes of our presentation. Hopefully within this time frame, we can understand more about how heat pump can be applied in our applications. Now, basically, a heat pump extracts energy from a waste heat source. All right. From this waste heat source, we can actually go through a refrigeration cycle. Basically, heat pumps works on a cycle very, very similar to any chiller cycles that you've come across, right? And you can see from here also basically from the heat pump cycles, which goes to the compressors, condensers, some waste heat will be rejected to the condenser side. And from the rejection of the heat, we can actually extract these in the form of hot waters, right? Which then contribute to the heating requirement to the plant or useful heating, right? So that is incomparable to, let's say, a boiler, which is actually doing a direct boiling, heating to generate hot waters through steam, right? Steam condenser and so on and so forth. So that will be the big major difference, right? Between a heat pump, which goes through a mechanical cycle, a thermodynamic cycle, versus that of a boiler. So that is a very classic and very simple definitions of a heat pump. Hopefully the audience will be able to understand roughly, right, this heat pump cycles works in a very cyclical manner. And the efficiency of the heat pump typically is definitely more than that of a boiler, right, which is a thermal machines in that case. So the benefits of a heat pump implementations, which I think Luke has covered a little bit just now, the broader aspects of heat pump implementations, is first of all, there will be some economic benefits and savings, right? So in operational cost saving from the use of boiler fuel versus that of a heat pump using electrical means to run the cycle to generate hot waters. So now in my studies of around all these heat pump applications and feasibility studies in food and beverage industries in Southeast Asia, we are seeing approximately 30 to about 70% cost saving, right? Depending on the kind of heating mode, the kind of temperatures, hot waters required, the capacities, and what kind of fuel, what kind of source of fuel they're using, right? So right from here, right, from the customer point of view, the dollar and cents, right, they will be first be captured and attracted towards this kind of benefits, right? So indirectly, in point number 2, as we reduce the cost of the fuel, the running of the fuel amount would also be contributing to the CO2 reduction and emission in the carbon footprint of these industries, right? And depending again on the types of fuel that these boilers are running, we could see something like 50 to 90% types of CO2 reduction, right? Be it small to big amount, right? Depending on the industry they're coming from. And that really speaks about the decarbonization step we are taking towards helping the environment, right? And that will be reducing our global warming initiative in most of the studies today around the world. And of course, indirectly, it also reduces water consumption as we heat recovered some waste heat from cooling towers or even condensers to produce useful heating on the other side of the heat pump, all right? And the third one is what Luke has mentioned, compliance with regulatory program around certain countries, first world countries, and also some developing countries which are coming out with net zero carbon initiative, and some companies which are going towards that journey of a net zero. Heat pump is a very intermediate step, or should I say a very big step towards carbon reduction, right, versus that of a boiler, right? So unless we are 100% using renewable source of energy, then of course the the benefit of the carbon footprint will not be there, but at least the cost saving of the fuel will be there, right? So these are the three basic classic types of benefits why we're implementing heat pumps. Now, a little bit of the types of heat pump. Some of the audience here who are new to heat pump technologies, I would say that heat pump has been around for quite a number of years back, right? In fact, in Europe and so on, right, heat pump is a concept that's been used constantly, right, because of different environmental, different applications. A very simple classic example is in our warm climate, we're using air conditioning system all the time, and we reject the heat to the outside. So that is actually a form of heat pump. We're just rejecting the heat from a cooling source to a heating source, right? Now, in the European countries' perspective, where there are 4 climates, and when it comes to winters, right, what they need is more heating than air conditioning. So they have to pump heat from outside towards the room inside to do heating, right? So that is a sort of a very basic understanding of a heat pump, where the useful energy is used for warming, for heating purpose, right, versus that of air conditioning. So with that kind of principle, you can see we can develop many types of heat pump, from using air as a waste heat to creating hot air as a useful heating, as air-to-air heat pump, or it could be water to air, which is using cooling water or wasteful water to generate some heat source and creating hot air on the other side, which is water to air heat pump. And of course, most of the classic types of heat pump you come across is water to water heat pump, right? Which is basically you can use all kinds of water as a source of energy and creating hot waters through the heat pump on the other side. So there are many types of heat pump existing in the market, from commercial types to industrial types, but basically the same principle applies, right? Which is to actually create useful heating from the waste heat source, or to do parallel cooling and heating at the same time. And you might also heard about something called a geothermal heat pump, which is very different from a geothermal energy source, right? Geothermal energy source digs very deep into the well to create, to dig out some high energy content for absorption chillers, for many other kinds of heating. Now, geothermal heat pump here actually refers to low-lying ground where you have some heat, waste heat source, some water source, which you can use it, extract it as a heat source, and from there producing useful energy for heating of the room, heating of the house, which applies mainly to many temperate countries around the world. All right, so just to give you some understanding about heat pump. Now, in terms of those who are a bit more understanding about technical understanding of heat pump, right? Heat pump and chillers operates almost on a similar cycle, except, right, chillers are operating at a lower temperature and lower pressure cycle to create chill water. So your chilling controls of the hot chill water temperature will be your temperature output, and that is your control point of a chillers. Whereas in terms of heat pump, it is operating at a much higher level of pressure to creating more hot waters on the condenser side. And as a result, your control points will be the hot water output of that chillers or heat pump, right? So that is the sort of the two basic types of differences, right? Some people got confused between chillers and heat pump. That is the basic definition. So chiller is for you to create chill water, your control points, while heat pumps create hot waters on the high side of the heat pump, right? Now, one thing to define about chillers efficiency, so heat pump efficiency, is we're talking about COP. So COP stands for coefficient of performance of a particular machine or chillers, right? So what it does is actually define, right, the useful work of a chiller or heat pump divided by the input powers, right? So it's actually a ratio of the output of the energy, right, divided by the input of the inlet shaft powers to the chillers. So in terms of the ratio, the bigger the number, it shows that it is more efficient to run a particular heat pump or chillers versus other kinds of machines. So if you look at the COP definition of a basic chillers, where let's say in this particular case, we have 5 units of cooling and 1 unit of input power. So the COP, so-called ratio of efficiencies of this particular chillers is 5 divided by 1. So you can imagine that it's 5 COP of 5, right? Now, if you look at the cycle of the chiller itself, so all this energy has to be rejected out to the condensers, right? And that will be 5 plus 1, which is the output of the heating. Now, if you want to define a COP of heating, basically the useful energy of 6 divided by the power input of 1 will give you the COP of 6 for this particular kind of heat pump, right? So that is individually being defined as the ratio of each cooling COP and heating COP. Now, many of us, or should I say, many of the practicing engineers today are looking at separately, right, which is cooling COP and heating COP. Now, if we combine these two together, and let's say we want to use this heat pump chillers to create cooling and to also create heating as another useful form of energy, then you can imagine that these 5 units of energy for cooling and 6 units of energy for heating can be combined together with just 1 unit of power. So that combined COP is much, much higher than that individually for cooling purpose or for heating purpose. So that is the overarching idea behind how a heat pump is so much more useful and so much more high efficient than that of a boiler. Okay, so these slides, if you're following me, the trend of thinking is the difference between, let's say, a boiler to generate hot waters versus that of a heat pump. Now, if you look at the diagram on top, right, it shows a basic boiler thermal machines which purely burn fuels to generate 100% of heat to the factories. So you are consuming 100%, in fact, even more, right, 110%, because the efficiency of any thermal machines in this case would always be less than 1, right, due to heat loss and many other kinds of losses in the boiler itself, right? And you have 100% emission of CO2. if you're using very unclean fuel, right? So this is a very unsustainable way of heating in any industry. So boiler is a very unsustainable way of heating, but the world has been has been using this practice for a long, long time, right? For many, of course, many types of reasons, right? And if you look at the comparison of a heat pump, right? Heat pump, which is the one that's below the diagram, you can see that instead of 100% energy being converted from fuel, you only use 25% of electric power, and the rest of the 75% of the energy comes from a waste heat source, right? And this waste heat source can actually come from a factory, because in any factory, there's always parallel cooling and heating at the same time, right? And some heat rejection. And if you can rechannel this energy back through the heat pump, and you can imagine that the efficiency of the heat pump is definitely much higher than of a boiler. And you can actually reduce the carbon footprint by going through a heat pump cycle like this. And yet at the same time, you create 100% of the process heat that you require for the factories, right? But of course, if you look at the heat pump technology versus boiler today, a boiler is almost a unparalleled means of creating higher energy, higher heat at any pressure and temperatures that you can imagine, right? Versus that of a heat pump, right? Heat pump has certain limitation, right? It will be able to create hot waters today, perhaps to 95 degrees C as a standard product. But we are doing towards more exploratory territory where we can create heat pump up to 120 degrees C hot waters, or even 165 hot steam, depending on the products that we're using, right? That's about the limit of the heat pump. Boilers can go beyond, right? 300 to even more, right? So that is also some pros and cons between what kind of heating temperatures we can get out of boiler technologies versus heat pump. Now, in general, as what Luke has mentioned before, heat pump generally have a slightly more higher investment cost. So what we can mitigate is by the energy saving through the heat pump, we can then get a much more better payback, right? And that's the reason why we are choosing heat pump now, to go that instead of using boilers for amount of heating that you have, right? So that is one of the trend that we're seeing, right? Initial investment cost of heat pump implementations. Then the types of hot water generating method, as we mentioned before, heat pump is going through a mechanical cycle to create heating, whereas a boiler is burning of fossil fuel, right, which contributes carbon emission. And of course, there are some boilers today which are using renewables, which of course will be contributing less CO2 or zero CO2 emission, but the burning of the fuel itself, the biomass biofuel, could be expensive, and it could be creating a lot of immediate soot at a time, right? When you're doing this kind of boiling, and it requires also a big footprint just to create these boiling efficiencies. And the efficiency of the boiler is always less than 1 again, right? And of course, in terms of CO2 emissions, it depends on the electricity grid that the heat pump is getting its electricity from, right? On average, right, from a factor of 0.4 to about 0.8 kilogram per CO2, depending on the kinds of fuel that we are using. Whereas, again, boiler depends on the kinds of fuel we are using. So in terms of COP, coefficient performance for heat pump is between 2 to 5 or even higher, right? 6 to 7, depending on the lift of the temperatures. Whereas that of a boiler is definitely less than 1, right? That's one of the major difference. Okay, so how do we apply heat pump? Actually, heat pump can be used for almost any industries that you can think of, right? Where you have parallel cooling and parallel heating at the same time. You can see that we have a lot of energy source in the factory, which come from air, from water, from ground, from even oil cooling, compressed air. There are a lot of compressed air in the factories where the compressed air oil has to be cooled down by radiator, by water. So this could be one potential source of energy which can be going through a heat pump to create useful heat for the various industries. So this industry could be from dairy, breweries, pharmaceuticals, boiler preheating. So you preheat the boilers before it goes up to the boiler itself, so saving some energy from the fuel. Refineries, which need a lot of heating. Meat processing plant, which need pasteurizations, reheating and so on. And even HVAC industry itself, because we know that in any AHUs, there is a humidifying process, there's a dehumidifying process, and also humidifying to control the RH through the use of hot water, so warm water in that case, and some air heating as well. So there's a diverse kind of industry we can actually apply a heat pump in this case. Now, I just want to share with you also a little bit about how we can actually generally apply heat pump, right? Through various types of schematic that I want to just illustrate, right? So for this particular illustration, we are talking about a waste heat recovery, where we extract waste heat from any condenser source, right? It could be a example of an ammonia condenser, which is typically for many ammonia plant around Southeast Asia, whether it's a food beverage plant, cold storages. And this excess ammonia would have been wasted to the condensers. But what if we could tap this energy, this waste energy, into our heat pump, which is what we call a cascade ammonia heat pump? And then we can produce, using this waste energy from the condenser side, we could actually produce hot waters on the other side of the heat pump condensers, right? For example, 90 degrees could be one source of hot water we could produce for process heating, right? So that's one way to actually tapping into waste energy source of the condensers. The other example on the right side, you can see, which is actually a cooling tower plant. So in many of the industries, in many of the commercial buildings even, right, there'll be many cooling towers rejecting heat of a chiller system outside into the environment. So what we could potentially use again is to tap this energy source, right? So pre-cool the cooling tower waters before it goes to the cooling towers, and use this waste heat to create useful energies for the process. Again, could be 40, could be 90 degrees, 80 degrees, 70 degrees hot waters, depending on the pressure level we are compressing on the heat pump, right? So these two are very, very classic example, right, to do waste heat recovery from a plant. So you would save energy from condenser fan, water cooling tower pump, and you could also save fuel at the same time, because then you relieve the energy of the boiler to produce hot waters, because you have some waste heat that you can produce to do this, right? So this is a very powerful combination of application on waste heat recovery through heat pump. Now, another classic example, it could be that if you can combine cooling and heating together in a process, right, in a plant. For example, the one on the left, right, it's a very sort of very matched capacity, which means that whatever cooling capacity you get out of the heat pump, which can cool water, for example, from 15 to 7 degrees C, and through that, you could also produce energy on the other side on heating capacity to what is required on the plant. Of course, this is a very idealistic way of matching the energy from cooling to heating, but if you can design, you can predetermine the outcome of this capacity, this outcome of this design, I think it is the best form of cooling heating that we can utilize the heat pump 100% energy input to do two types of benefits, which is cooling and heating in parallel. So that would be a very, very useful use of both cooling and heating. The one on the right-hand side, it's very kind of like practical experience to some plant where you may have some existing plant which is already doing cooling, and you're also doing a boiler at the same time doing a heating which is separate, right? So how do we link them together is by tapping or pre-cool some of this cooling energy from a plant before it goes to the existing chillers, and utilize this cooling, right, pre-cooling, I would say, and then generate hot waters on the other side on the condensers. So again, it can reduce your existing chillers operation energy, and yet at the same time also reduce your boiler fuel consumption on your existing boilers, right? So this is really a dual saving, right? Plus, of course, some other saving on the cooling towers and water pump as well. And it is really a powerful application, again, to tap into the kind of synergies you can actually produce parallel heating and parallel cooling at the same time. Of course, there are many ways of tapping this heat pump to apply, depending on how high the hot water temperatures you need on your process, and whether you are needing this cooling water for any other applications. Here is one actual example where we could say we could tap into an air, right, free cooling of the air through AHU, for example, and you produce chill water to pre-cool this AHU, and from which you can scale up to more bigger capacity, more bigger heating capacities on the other side, whether it's for pasteurizations, for clean in place, for product heating, oil heating, syrup heating, all kinds of heating on the other side of the end, right, could be done by this heat pump. So even though the free cooling of the air is a byproduct of this heat pump, but at least this cooling air could be used for many of the factories around Southeast Asia where the environment is hot, right? So this is one useful way. But of course, the focal point of control here is the output of the hot water temperatures rather than that of the free cooling. Another example I can show you is, let's say, if you need the AHU to control your room temperatures, and you also need some dehumidification or RH controls on your heat pump, on your AHUs. Typically, what many of the industries are using are either using boiler steam to control the RH, or they could be using some other means of warm waters. Now, through the heat pump here, right, which is actually producing chill waters to cool your AHUs, you could also produce parallel warm waters or heat recovery, right? About 45 to 50 degrees C that can go into the AHUs for the drying effect, right? For what we call the RH controls. At the same time, some of this excess hot waters could also be used for shower, for laundry, for cleaning, right? So just this typical example to show you the kind of benefits we could get of a heat pump combination. Now, in terms of our product portfolios, heat pump compressors has many types, right? From scrolls to centrifugals to reciprocating compressors. And you can see here, heat pump has all kinds of temperatures we can develop, right? From standard temperature hot waters to high temperature hot waters. So for standard temperature hot water heat pump, you could actually use any of the Freon, any of the refrigerant, or even HFO refrigerant today to do the heating, right? And of course, more higher temperatures require more higher pressure compressors in the form of, and we'll be using also more natural refrigerant, which is ammonia or even waters to produce very high temperature heat pump applications. So they'll just give you a flavor about our product kinds of development in terms of heat pump, right? And this is the kind of air to water heat pump which we have also in the family, where we can cool the air and generate hot waters on the other side. And also some water to water heat pump, which is using primarily some HFO refrigerant for lower heating temperatures, about 50, 60, maybe to the highest about 80 degrees C, depending on the types of screw, high pressure screw we're using. And a bit of some customized heat pump as well for some very large heating a high temperature profile. You could have multi-stage centrifugal compressors that can generate hot waters up to maybe 90 degrees C. And in terms of capacity, scale it up to about maybe 5 megawatts to 20 megawatts of heating capacity, mainly for district heating applications around European countries, and perhaps maybe in the future to come in China as well. We're doing major district heating through the use of heat pump. And to be more sustainable in the futures, as we know that we are moving towards the direction of more sustainability, ammonia heat pump is also a very classic example of how we can use heat pump to generate hot waters up to about 90 to 95 degrees C, right? And it can cater for very large water delta T on the heat pump on the hot water side from maybe like 30 degrees to about 90 degrees. So that's a very useful application of a heat pump in this case. So heat pack, our product, in this case, using natural refrigerant, ammonia, we can preheat waters to about 90, 95, and we can also pre-cool waters or heat recovery. And if you need a heat pump to do parallel cooling and heating at the same time to low temperature, 5, 10 degrees C, and high temperature to about 90 degrees C, you could even have a two-stage heat pump, which is a dual pack in our sense, to do that kind of parallel cooling and heating at the same time. Now, let me share a couple of case studies, which will be more interesting for us to really understand how we can apply this, right? So I have a couple of case studies, which hopefully I will be able to illustrate through, right? One of the cases I've done is in Indonesia, right? Where we are using heat pump for laundry, CIP, and some dairy hot water requirement. So this customer has a huge amount of boiler fuel, right? That is doing boiling for pasteurizations and many other things, right? And we are using about maybe 10% of that boiler fuel, right? To do water, hot water from about 27 to 90 degrees hot water applications. So that translates to about maybe 308 kilowatt in terms of the heating capacities. So we are using some waste heat source from the ammonia condensers to generate this kind of heating. And through the COP of the heat pump, which is about 4.1 in this case, when we select the heat pump, we have some annual heating capacities and also annual cooling capacity we can extract from the existing ammonia plant and produce some sort of heating for that. So with this annual consumption of heating and cooling at the same time, we can also do an equivalent CO2 and also energy consumption from the boiler and the fuel consumption from the boiler, right? So just bear with me a bit for the small print. What we have here is actually a comparison between a boiler fuel consumption and the heat pump and electrical consumption to do the same amount of heating at the same time. So from the characteristic of the fuel, which in this case is methane natural gas, compressed natural gas, and the electricity bill that we can build out of this particular location in Indonesia, for example, we can actually do a parallel cost study between the two types of fuel consumption. So we are seeing roughly about 60.9% of annual cost energy saving in terms of the fuel between a boiler fuel in terms of natural gas versus that of an electrical source, right? And that contributes to a certain amount of energy saving and cost saving in terms of fuel versus also the investment cost of our ammonia heat pump in this case. So we have roughly calculated to be a payback about 5 to 6 years, depending on the cycle of operation of the heating and how often it's been implemented. All right. And at the same time, we also see some CO2 tonnage saving in terms of about 28% in this particular case. Right. So for this particular Indonesia customers, interesting to see is the kind of cost saving, the kind of payback, and the kind of carbon saving we have. Now, coming back to a Singapore case, right, where fuel costs and energy costs are very much different from Indonesia, right? And I've chosen one particular case study in Singapore where we have a heat pump on hot water processing, right? So let's say this particular case, we are heating water from 57 to 80 degrees C, and these waters are recycled back for reheating purposes. And we have, let's say, about 40 million cube of water to be heated up, right? And we, in Singapore, most of the time, the boiler are normally using compressed natural gas. And then we have a heat source. In this particular case, we are using a parallel cooling methodologies. So this is an existing plant where there's a chiller that's running about 300 tons of chillers running chilled water at the same time. So we are trying to use heat pump to pre-cool the water, right, at the same amount of temperatures and extract this cooling capacity to generate hot waters on the other side for 80 degrees C hot waters. So you can imagine that we are putting in a kind of a heat pump to do both cooling and heating at the same time to create both synergy of saving, right? So based on this and the selection of the heat pump in this case, actually we can use our standard product for HFO heat pump, high heat temperature heat pump to generate the hot water up to 80 degrees and cool water down to 7 degrees. And again, we are doing the same kind of parallel studies between using boiler and using natural gas with the current Singapore rate of about 0.3247, right, Singapore dollars per kilowatt of the electricity rate, and the boiler fuel about 2.4 Sing dollars per kilogram of mass of this natural gas. We can see something like a 38% cost saving, right, which translates to quite a large amount of energy if you look at that and the cost of the fuel, right? So, and with the kind of carbon saving, we are saving something like 33% of the carbon footprint of the boiler fuel using natural gas versus that of electricity grid from the Singapore Power, right? So these two savings here, right, these two kind of saving is kind of like significant for us towards a step of lowering the energy costs of the fuel and also the carbon footprint. And in terms of the payback, actually it's quite interesting as well, depending on the types of heat pump we are choosing and selecting. We are seeing less than a year kind of payback. So it's kind of very, very attractive for us to really go forward to steps of doing these heat pump case studies. All right. Another case I've chosen, it's in Philippines. In this case, is a brewery plant. I think some of you have known Philippines is famous for many brewery plants around producing breweries and so on, a very famous brewery. And they are looking at producing hot waters up to 85 degrees C hot waters, right? About 20 million cube per hour of water consumption. And this hot water, for some reason, has been mixed with the products and so on, and it's not being recycled. So, and they have to produce using steam condensers to produce hot waters from a city water temperature about 28 degrees C to about 85 degrees C. So again, we have some waste heat source in this plant, which in this case is a cooling tower plant. So we extract the cooling tower waters, cooling it from about 36 to about 30 degrees C, and from which we can generate hot waters from 28 to about 85 degrees C. So the same reasoning again, choosing a heat pump with a very high COP of 5.5 on heating side and the electric power it can consume. So we again do a very parallel kind of a study between a boiler fuel consumption doing the same heating process versus that of electrical heat pump. Again, we see a kind of a 38% in terms of fuel cost saving and carbon saving of close to almost 59% in terms of the carbon footprint emission saving between that of a bunker fuel in the Philippines versus electrical power generated from the plant itself from Philippines. So we are seeing something like with the investment of ammonia heat pump, we are seeing something like 1.5 to about 2 years on average, depending on the operating hours, depending on how much they are, the load cycles of the heating, and so on and so forth. So these few interesting case, right? And I compile with several kinds of customers we have come across Southeast Asia, right? I've compiled here a number of cases, a number of industries, the types of fuel we're using from diesel boiler with coal, right? Compressed natural gas, And the kind of heat source we are getting it from, whether from cooling towers, condensers, and the kind of hot water temperature we're producing, the annual heating capacities of these particular customers, and the emission grid factors, right, which affects the amount of CO2 produced from the electricity of use in the heat pump, and of course COP, and the kind of energy we can save, right? So you can see, interestingly, there are varying factors that's varying the kind of payback that we have for our ammonia heat pump. So we have a range of maybe 2 years to about, sometimes as far as 8.5 years, because those longer year period typically refers to customers who are using very, very cheap coal, right? Which is like coal, and it's a dirty fuel, right? So that, and also the emission grid factors as well. So you can see this is actually a very interesting feedback and interesting compilation of all the study we've come across different Southeast Asias in the study that we've done. All right. So a bit of a couple of more slides just to show you, if in case we are able to go beyond the standard heat pump of 1995 degrees. JCI has actually developed a technology by acquiring a new company called Hybrid Energies that can give hot waters pressurized up to about 120 degrees C, right? The intention, of course, is really to relieve a lot of the energy goes through that has been using boilers as the means of generating hot waters. So hopefully by doing more R&D, more exploration, we are able to reach more higher and higher hot water temperature heat pump or hot water steam heat pump in the future to come that is able to relieve what the job has been done by the boiler, and hence reduce our carbon footprint in use of boiler fuel consumption. And a couple of plant that we've installed around European that is using very high hot water temperature heat pump around the world. All right. Now, my last slides, just want to share with you that the heat pump market overview in terms of where we are. All right. We're seeing that a lot of the heat pump market has been growing very fast in Europe, especially during the war crisis where natural gas has been shut off. So we had to use very intensified energy source to do heating, especially in those climate countries where heating is more required in the cold seasons. And also China, the big country, Northern China and North America. So these are a huge growth in heat pump, mainly because of rapid energy demand, right? And fast-paced urbanizations, industrializations, increased investment in energy-intensive infrastructures, and of course, many positive outlook because we are pressing for minimizing carbon footprint in all these developing countries, right? But we see that APAC and Southeast Asia is lacking in terms of the heat pump development. I guess there are many factors that contribute to this, right? First of all, the difference in our climate conditions. Here, we are facing a lot more hotter and humid environment compared to a cooling country, a cold country, or a temperate country, where heat pump is required to do a lot more heating than this part of the world, where we use more on the cooling for air conditionings, right? And of course, the energy cost difference, right, between here and Europe, as well as any other part of the world. Our energy costs are relatively cheap, let's say, compared to European and other countries. So that's why the adoption of heat pump is a bit less, much more less, right? And of course, traditionally in APAC, in Asia Pacific, Southeast Asia, there's a lesser awareness of heat pump advantages in APAC. People are not aware what is heat pump, right? So we've been generating this interest for the last 2 to 3 years to create more heat pump awareness because of the carbon global warming effect of using technology which are creating more boiling, all right, through boilers. So we are creating this awareness right now to the advantage of heat pump. And of course, the other thing is the lack of understanding of how heat pump installation can be done, right, in a conventional boiler system, and how do we verify the energy save, energy verification methodologies. So these are still in a very early stage of our applications. So I believe as more and more of these heating applications being applied, we will have a more mature kind of technology to measure and verify the saving that we have. But as an example, the feasibility studies already give us some indication of very powerful saving, a very powerful payback, right? And we also face challenges of the changing of the current steam system in our APAC and our steam in Southeast Asia to heat pump applications. So customer has to get understanding how do we integrate heat pump, right, to that in place of a steam boiling system. Because many customers today in Southeast Asia are very used to boiler as the means of heating. To do away with that, to change to a new way of heating is a mindset change, right? And they have to see the benefits out of that through feasibility studies to energy verifications. And some of these customers are facing also challenges in terms of the long period of payback of heat pump versus the boiler, right? especially with government fuel subsidies in some countries. We see that even more, right? So we hope that through the more efficient development of heat pump, targeting at high temperatures heat pump, and the carbon and the government initiation towards more carbon tax emissions, curbing of carbon emissions, we will see more and more customers turning towards heat pump as a means of reducing carbon, reducing costs, and getting some very good payback in terms of this. And of course, Luke has mentioned that we have JCI capital financing that can actually help customers to develop and purchase heat pump so that in the long term, they see the benefits of heat pump creating, reducing carbon footprint and reducing energy consumptions in the long run. So with that, actually, just want to finish up by saying thank you to your attentions. I'm Chia here. You call me Chia. I'm based in Southeast Asia, and we have also some other experts, Louis, who is another expert in our JCI office, and of course our industrial leaders, plus of course Luke here, who is able to also educate how we can help you in the journey towards decarbonization. So thank you for your attention.
Thank you very much, Peng Kiang. Well, gentlemen, ladies and gentlemen, we are very fortunate. Obviously, Peng Kiang knows a lot about heat pumps. He's definitely the technical expert. And we have quite a number of questions that have come in both when you're registering for the masterclass as well as live questions. So we have time to take some of these questions. Luke, can I also invite you back on the screen if your microphone's also turned on? So the first question I'd like to take up here would be, could you give examples on the emission reduction potential of this technology and its cost? I believe, Peng Kiang, you had shared some of it, but whether Luke or Peng Kiang, you wanted to add a bit more flavor to this question.
Yeah, sure. Yeah, thanks for the question. So in terms of emission reductions, as we see, it depends on the types of fuel, right, the boiler are using. So the more unclean the fuel is, of course, the more emission of the CO2, right? And we are also seeing some trends of customers applying what we call biomass boilers. So of course, biomass boilers is good in terms of CO2 reduction, which means it's a renewable, there's no CO2 emission. But again, a boiler is a boiler. It's an efficiency less than one, right? Compared to the heat pump, we have a much better high efficiencies. So in terms of boiler fuel consumption, I would say we will still reduce your fuel consumption, especially if you're using expensive biofuel, right? In some country where there's no biomass and biofuel. So I believe we can still save energy cost consumption, even though there is no CO2 emissions, right? So it really depends on where the country is based, how the boilers be using their fuel, and how energy efficient we are producing our heat pump for that kind of applications. So in general, that's kind of a trend we're seeing today.
Okay, great. Now, another question here. What is the biggest challenge to apply heat pump over traditional boiler in Southeast Asia? You have mentioned a few of the reasons, from cost, which, it's more expensive and it's longer payback from a traditional boiler. But of course, you also gave some examples, 60.9% cost savings, right, in one of your case studies. But other than this, any specific big challenges that you think is really hard to overcome for heat pumps in Southeast Asia?
Yeah, sure. So there are even some cases where I've studied they're using coal, right, a very cheap source of coal, and the payback is long, maybe more than 6 years. And immediately the customer says, well, it's too long, I wouldn't invest. But when you look at the carbon footprint saving, is tremendous, it's 50%, right? But that's not going to move them. So one of the challenges is that which priority they're putting on this. If you look at dollar and cents, they're going to put back this investment. But they look at carbon footprint emission. Yes, some company will say, yes, I'm the first one, I'm going to do it because it's going to reduce my carbon footprint, it's going to reduce my carbon tax. By the way, Singapore carbon tax is $25 per ton. Well, that will be excised into the duty of the electrical bill we're paying anyway. So the more you use, you're going to pay more carbon tax. But in many countries, there's no carbon tax. I would say in the whole of Southeast Asia, there's none, right, other than Singapore, right? So if we don't penalize this, right, then customer will look at dollar and cents. They will not care how much carbon they're saving, even though we know the world is actually going to the brink of approaching more than 1.5 degrees C due to global warming. So this is a very intensive message that hopefully the government would follow regulatory meetings to really curb CO2 and not just dollar and cents. And besides that, we are seeing now better and better payback with advanced technology, more cost reduction in our production. We're able to cut some of the costs to be more competitive. So as heat pump becomes more, I would say production ramps up in factories. I'm sure the cost of producing will be lesser, and hence increasing the adoption of heat pump. So hopefully through that and the payback we're doing, it can justify, because electricity rate is going up, fuel costs going up as the resources of oil is getting less with the war and so on and so forth, and we are seeing more fuel costs is going up. So I guess with this kind of situation we are facing, we can overcome the challenge of first cost versus long-term carbon saving versus long-term cost saving in the terms of payback.
Right. Staying on that topic of cost, there's a question here that would like to know more about the cost of technology, investment, and operating costs for some industrial use cases. Luke, you also mentioned earlier that there is a capital financing within Johnson Controls. Perhaps you might want to touch on that.
Yeah, sure. Just give me a second. Can everyone hear me okay?
Yes,
Yep.
we can.
Okay. So I think so first to address the cost question, I mean, it's very subjective. We're doing deals at the moment from anywhere between 300K up to 700K. It can be a lot less. It can be, significantly more, depending on what the application is. But I think it's not just about the availability of financing and the high upfront capital costs. I think it's also about how you structure the deal. So one of the things that we're seeing as market practice, and we're also kind of exercising ourselves, is trying to come up with better structures. So we see things like heating as a service, or cooling as a service, where you're actually looking at performance-backed structures that are financed by project finance, but we could transact in refrigeration ton hours and look at it that way. We're seeing a lot of that in the market right now. So I think number one, it's important that this becomes an OpEx reduction solution for the customers, meaning whatever they would have been spending on fuel, it is more than what their monthly payments would be on a finance deal. But also, going a step further, how do we charge for that, and what performance do we give? I think the important thing to mention here is when we go through this deal process, and the final implementation typically sees that the boiler's still there and is there as a backup solution, and that the heat pump is offsetting that fuel usage. So there's some redundancy there. So I think we're gonna start seeing some different structures and some different ways of thinking about it. Going back to what Peng Yang was saying about mindset change, asking someone to pay $700,000 up front for a technology that's more complex than a boiler is not a straightforward ask. But if you present the engineering solution, you present monthly repayments that are less than their current operational costs, and then you do the structure in a way that takes some risk off the client, and I think it changes the whole deal making process.
Okay, great. Now, I'm very mindful of time, but there's quite a number of questions. So what I'll do is I'll just extend this for about 5 more minutes, and I'll take 3 questions from the live audience here. And one of it actually relates to what Luke just said, right? You can still retain your boiler as a backup, but and this, of course, means that people would need to know what is a typical footprint of a heat pump, because whether their current facility can still add, have a space to add that heat pump.
Okay, yeah, I can understand that. So a heat pump is quite similar to a chiller. If you look at ammonia, a Freon chillers, HFC chillers in any mall and so on and so forth, right? I would say for the ammonia heat pump, for example, a very compact one, right? Typical heat pack, we are talking about 4-5 meters long and about 1 meter width and about maybe 2.5 meter high. compared to a 5 to 10 ton boiler, the space required for a heat pump is much, much more compact and lower charge, right? Refrigerant compared to that of a boiler. And of course, you do have to insulate, you do have to do a lot of insulation. Boiler need a lot of insulation, a lot of piping around, fuel piping, water piping, steam condenser trap, and many other things. So in terms of space, I would say heat pump is definitely much more compact than that of a boiler. Of course, in corresponding, we also have HFO, HFC heat pump, which acts almost like a chiller. So that kind of footprint is kind of like very acceptable in a typical machine room, in the buildings, in the factories. Yeah.
Now, related to that question, and this is also something that we will be discussing in the International Built Environment Week conference that will be happening from 4th to 6th September, which is about retrofitting, right? Do you have any tips on retrofits in district heating? For example, old buildings versus new buildings that were not designed for heat pump. What's the cost and benefits like?
We have not actually done any district heating studies, whereas in Europe, I think we have done a lot of case, and that is probably sitting in our center of excellence in Europe. Definitely, we can borrow the expertise to lay it over in Southeast Asia. I would say the consultant in general in Singapore context, when we talk about district heating, is something new, but not new in China and some of the bigger countries where district heating is required. So the expertise will probably sit around those areas. But we can chip in, right, with the help of our product and the help of our payback studies, together with the consultant, together with the contractors, to look at what kind of scenarios, right, we can play this into those district heating, right? Especially Singapore is adopting district cooling right now in a few sites. But we have not really done any district heating because Singapore basically need more cooling, let's say, compared to heating. But let's say in other Southeast Asia countries, if heating becomes a major source of requirement for various industries tied together, that would be an interesting case. Hopefully, we can get onto those cases. Yeah.
Yeah, okay, great. Now, I think this is also a question that, because the name is heat pump, right? There's a lot of, well, whenever I read these, people always get confused. What can a heat
Yep.
pump do? So now the question here is it true that you can only use chillers for space cooling, whereas heat pump is only for making hot water in Southeast Asia? Very
Okay.
common misconception.
Yeah, I guess in the earlier slide I've showed you can combine cooling and heating at the same time. So a chiller just do chilling, right? Whereas the heat is wasted out as a cooling water, right? But if you use that cooling water, or if you use a condenser water for heating purpose, and you generate even higher temperature through a more high compression on the heat on the compressor side, then it becomes both heating and cooling. And then therefore the heat pump definition becomes a mix, right? Because you're doing heating and cooling. But if you're focusing mainly on heating as your output, that is a heat pump. If you're using that as cooling as your output, that is your chillers. But these two actually, I would say, is intermingled, interchangeable, right? Depending on what is your output requirement. Is it heating that's what you want or cooling that you want? But bear in mind, it can do both. You can do both cooling, you can do both heating at the same time.
That's right.
Yeah.
Okay, so I hope that addresses that misconception so we don't waste the heat, heat that has
Yes.
been generated. Now, would performance of a heat pump be affected by poor ambient air quality such as transboundary haze, as well as would the increasing ambient temperature affect the efficiency of heat pumps?
Okay, I think that's an interesting question. I think I will address the second one, talking about whether the ambient temperature will affect heat pump. Definitely yes, right? So if you imagine that in Europe itself is mainly cold temperatures, the heat pump actually had to work harder to cool the air and then extract the energy for generating hot waters. Generally, their efficiency will be lower. Now, in our environment, which is actually warm, we have plenty of warm energy to be tapped, to be cool, right? In fact, our efficiency is even better for air to water heat pump in this part of the world, right? That is where we extract high energy because then your compressor doesn't have to work so hard to lift it up to a higher energy source to create hot waters. So that in a way answer that, whether it's low, the lower the air temperatures, the more harder the heat pump has to work, because it has to cool at lower air temperatures to generate hot waters on the other side. Okay, the first question about transboundary haze. Of course, if you use a radiator or use anything that extract heat, right, this will be tainted by all these particles of air that get clogged into this heat pump. That will reduce the efficiency of the heat pump because then there's a layer of dust that is impeding your energy transfer. Of course, then we will put in what we call AHU, so that at least some of the AHU filters will be able to filter off whatever particles, and then you have a free air cooling by the actual coil itself. So one way to bypass it is to have a good filtering system with an AHU to reduce the kind of particle haze that is coming in. But of course, this is not going to be a long lasting, right? If you continuously having haze every day, then you have to clean your AHU like mad. So hopefully, it will clear off whatever air particles, the bigger one, at the first stage of the pre-cooling or pre-filtering before it goes to the coil. And constant cleaning will be required for this kind of environment. Yeah, which is probably much more happening in Southeast Asia than maybe anywhere else. Yeah.
Okay, I'm afraid that's really all the time that we have today. For those of you who have submitted questions that during the masterclass and it was not picked up, my apologies for that. But do not worry, we will be sending these questions over to Johnson Controls and they will be getting in touch with their answers to you. I see there's quite a few questions here. What if we do not use boilers? What's the payback like? And I also see a question about different types of applications. So this kind of questions, you will be getting an answer from Peng Kiang and the team at Johnson Controls. You also can see on screen right now the email addresses of the experts from Johnson Controls on heat pumps. So drop them an email. There's one here who said they want to get in touch with you because they have an application with high heat exhaust air of above 400 degrees Celsius. So ladies and gentlemen, thank you very much for joining us today. Luke and Peng Kiang, thank you very much for your time and your expertise. Ladies and gentlemen, do not forget that we will be having BEX Asia in the 16th edition of the largest built environment show here in Singapore for the region, as well as the International Built Environment Week Conference, which will cover some of these topics such as retrofitting, which I mentioned earlier. It will be happening from the 4th to 6th of September, so do keep in touch with us. Make sure you are subscribed to our newsletters. And we'll see you again in our next masterclass. Thank you, Peng Kiang. Thank you, Luke. And thank you, everyone.
Thank you, Suhaimi, for hosting. Yeah, thank you.
Thank you.